Columbia Astronomy.
And Bill.
And what?
Don't forget me.
Oh,
Yeah.
yes, I'm sorry. Two speakers here. Can I just hit play?
No, it gives you the last slide.
That'll get, okay, then you do it. I'll take it.
No problem.
Duane's going to talk about reconstructing the galactic halo's accretion history, a finite mixture model approach. Let's hope it works. Yes?
I don't have the notes. Amazing. Here. Right, so somehow. Oh,
Yes, that'd be good.
Yeah, but did he- that's
Okay, take off.
that's it. Okay. Perfect. Yeah. Yes. All right, hello everyone. I'm Duane Lee, astronomy graduate student at Columbia, working with Jessop and Sen, who are in the CESS department at Columbia, and my advisor, Catherine Johnston.
And Will's going to give the second half of this talk, right?
And Will's going to be at the
Sorry, I didn't introduce you.
Yeah, sorry. Okay. So what we have here is a picture of the Andromeda Galaxy. And what we can clearly see in this image is the bulge of the galaxy and the disk of the galaxy that has some gas and dust lanes and some evidence of star formation in these little purple regions here. But for the purpose of this study, in terms of trying to determine the accretion history and really the formation of the galaxy, the component of this galaxy that is present but just not visible here is, in fact, the galactic stellar halo. And so that's a large component of stars, a small percentage of the total amount of stars in the galaxy, but this large spheroid that exists around the Andromeda Galaxy, as well as the Milky Way, and essentially all galaxies that we see in the universe. And what's interesting about that is because there's so few stars in the halo, for a long time in astronomy, there's been a debate over two particular modes of galaxy formation. One being the monolithic model, and the other one being the hierarchical model. And the reason why is because it's taken so long, and only until more recently, say the late 90s, and over this last decade, were we able to really get some fine information here. So just to point out what the monolithic model is, essentially, the monolithic glass models that you have this large gas cloud of hydrogen and helium that collapses over time, and as it does, it starts to fragment, and those small fragmented pieces become your stars in the galactic halo. And then eventually you have the flattened disk component of gas that will form stars in the disk and a bulge and this whole galactic halo. Now the other model, the hierarchical model, is the idea that you in fact have these small galaxies that essentially just collide into each other and gives you a bigger galaxy. And so those are the two modes of galaxy formation. And in fact, to show you here that one such mode we believe is more dominant than the other. So here I'm going to show you a simulation from my advisor's work, Catherine Johnston, along with James Bullock. And what you'll see is that in the center you have a disk that represents the galactic disk, and it has some gravitational potential due to that central disk. And as the simulation goes on, you have all these satellite dwarf galaxies coming in and then merging with the galaxy in the center and forming this large spheroid that you would consider the galactic halo of that system. Okay, and if I run this again quickly, what you should know is that each of these dwarf galaxies have different colors to allow you to see how the distribution of the stars that belong to them is redistributed. And so we start to see features like tidal streams wrapping around the disk, and these splashback events of stars as they go through the galaxy and then come back. And so what's awesome about this picture is that, in fact, when we look at observations, we see these same sort of features. So this is a observation from the PANDAS team. So this is like Pan Andromeda survey, essentially, which looks at star counts around. So this center part right here, this small part, would be the optical disk that I showed you before of the Andromeda galaxy. And so so they took this survey, and so you have essentially star counts in and around Andromeda, and what you find is, in fact, there's evidence for hierarchical emergence. So you see that the stellar halo has substructure. So in the monolithic collapse model, essentially when you form this, because this is all kind of random fragmentation, you should have a smooth halo. You shouldn't see any substructure. So this is seeing the substructure as we've seen in the Milky Way, but this is even more impressive to see a number of loops and actual dwarfs that might belong to these actual tidal tails and streams, that this lends almost definite credence to hierarchical merging being the main mode of galaxy formation. And so what's also cool about this is that you can use dynamical models, such as the one that I showed previously, to try to extract the recent accretion history. So you can actually run these streams back into time and find the coherent galaxy that was a progenitor to these streams and some of these overdensities. And so that gives you some insight into how the galaxy actually formed. And that informs our ideas about many different aspects of galaxy formation and even the evolution of the universe as a whole, because this has to fit into that larger cosmological picture. Unfortunately, there is a limit to which we do with that sort of technique, and that has to do with this phase mixing, which limits how far you can actually run this information sort of back into time. And that's essentially because these streams over time will get washed out, and certainly in the simulation you saw that some of the earlier dwarfs that fell in essentially started to form this kind of more smooth halo component. So this is a snapshot from those same simulations that I showed you before, and this is just once again to point out that we do in fact see these features in the simulations, that closer in you start to get maybe more of a smooth halo distribution. So this would be galaxies that fell in early on, where most of their signature of coherence is kind of been washed out, and then further out you find plenty of dwarf galaxies that have yet to fall in and really start to interact tidally. And so these simulations were cosmologically motivated, and these are surface brightness maps showing the distribution of stars. So, knowing that there's this limit to what you can do with these surface density, phase space sorts of data, how can you press even further back? How can you infer more from the information we get from halo stars to figure out more about galaxy evolution in our own galaxy and galaxies nearby? And so what I'm showing here is, in fact, a way to achieve this. So this is a 2D metallicity plot. So on the y-axis is alpha over Fe. So the alpha elements are things like titanium, magnesium, and calcium. And then Fe, of course, of H, iron over hydrogen. And the physics behind that behind these two axes is not so important to the overall point. Just note that these are two different ways that you can measure the amount of chemical enrichment that has happened in these stellar systems over time. And so what I really want to point out here is that stars actually remember their genetic history. That's to say that the chemical abundances that they inherited from a previous generations of stars via the supernovas that went off in that past star formation event is then transferred to any stars that are now formed out of that new gas. And so that mixture is just then locked up into the atmospheres of those stars. So when we study them and we split up the light spectroscopically, we can then measure these different abundances in the stars. And so if that's the case, then it doesn't matter when those stars fell in. You can, in essence, at least in principle, essentially identify them with a particular body of stars that they grew out of, were born on. And so here on this plot, you have a number of stellar data points. This is observations from the halo and from some low mass galaxies, so on and so forth. But the main thing I want to point out is that their distributions are spread out in this 2D plane. And so they do tend to occupy certain regions of this 2D metallicity space, precisely because of the specific nature of the environment that those stars were born on, and that's actually tagged to the type of galaxy or stellar system that they're related to. And so that gives us some information about the type of system, dwarf galaxy that they belong to, but also pointing out that, for instance, this is a low mass system, whereas systems here are higher mass dwarfs. And so you can also start to look at this in terms of for instance, the mass of the progenitor, or the mass of the galaxy that they belong to, actually affecting the types of stars that they create. So understanding that we can start to have this information, see these relationships, you can now go back to the models that I showed you earlier, and I'll point out that they also had a semi-analytical treatment of metal enrichment in those models via the star formation. And so if you haven't kind of noticed already, the colors here represent the mass of the galaxy to which they belong. So purple to black is low mass, blue then to green, yellow, and orange is higher mass. And so the same sort of situation that we saw in the observations, where low mass is here, higher mass is here, is what we we're able to reproduce in the simulations, even with what's considered a simple treatment of chemical enrichment. This is by no means the most complicated approach to tracking chemical enrichment or producing it in these simulations. So, knowing that, how do we take that information and then apply it to, in fact, be able to have a better reconstruction or a more complete reconstruction of the accretion history of the galaxy? So, in those simulations by Bullock and Johnston, we have 11 halo realizations. And in those halo realizations, we had 1,500 simulated accreted dwarf galaxies. And so in each one of those dwarf galaxies has their own chemical enrichment history. And so that's signified by these tracks, which are tracks in this kind of average metallicity enrichment over time, where the colors kind of represent the relative number of stars that have a particular chemical abundance in this 2D space.
So by 1,500, you mean 1,500 per realization?
No, I mean 1,500 total.
Overall realizations.
Overall realizations, yes. And so each halo has a subset of that 1,500 in them. And so the idea is that you go from these halo realizations, you have these 1,500 possibilities in terms of how your dwarf galaxies will look, in part due to their mass, and also in part due to the fact that once they're accreted, star formation is cut off. And so that's also another key point of this model. And what you could do is you could take galaxies that have similar chemical enrichments and have similar, that have similar masses and similar accretion times. And what you find is that generally they have similar chemical enrichment patterns. And you can bin them together to get some sort of average galaxy for a particular accretion time and a particular mass. And from there, you can start to form this set of templates that are going to represent particular galaxies accreting at particular times. And so the idea here then is by doing that, depending on how you want to go, you can actually set up this master template, a series of these dwarfs that have various characteristics based on their mass. So on the y-axis here, you have bins of 10 to the 8 to 10 to the 9 solar masses, 10 to the 7th to the 8th, so on and so forth down here.
So this is the masses for each of the dwarfs?
So it's the masses for each of the dwarfs, yes. Okay, and then the stellar mass. And then on the x-axis, you have the accretion time. So you have from 0 to 2 gigayears, so that's recent, and then 2 to 8, 8 to 10. And so, just to point out, this particular master template was kind of made with a kind of a best guess as to how some of these things would break down, but by any means, it's not the most optimal way of slicing or bidding up these accretion times and masses per se. But what you do see is that when you do this, you're able to recover certain relationships that we've known to exist for quite some time in astronomy. So that's, for instance, the mass metallicity relationship. So as you go from lower mass to higher mass in this one time column, you see that things become more metal rich. And just to point out, this is a logarithmic scale, so 0 is solar metallicity. And so over time, things become closer to a solar metallicity. And then also in the looking at a particular mass, what you're able to get is a difference in your alpha abundances. So you find that things become more alpha enhanced as you go back into time. This is something that we also see in our own galaxy. When we look at the galactic bulge, we believe that that was formed early on. That's actually alpha enhanced compared to stars in the disk. So
More
these are
metal rich.
yeah, well, yes.
Just seeing the term.
Yes, sorry, yes. More metal rich in this measure. Okay, so the question is sorry, how do you go from this master template, apply it to, so this is Halo 2 in our realizations, to this distribution of what are observed stars from the halo, to then get this output. And so this output would actually be the accretion history of this halo. And so that's very important. What we're looking for is that you put a certain master template in, you apply it some way to your actual data, and then it spits out what it believes is the best ratio for luminosity contribution from these different satellites. And from the luminosity contribution to the halo, you can then start to look at quantities like the number of dwarf galaxies of this nature that fell in, so on and so forth. So the real key here is this is a way to get past that dynamical kind of wall in terms of how far back you can look into time and try to infer the actual formation of the galaxy.
You've got 16 there, right?
Yes,
and
right.
You're covering a lot of the parameter space. So I'm sure it's not hard to find a model that will work.
Right. No, that's true. So like so this is well that is in fact the case. So in this case, I also point out that the numbers actually work well because this was a test case. So this was the case where we took the actual accretion history and applied it to the halo and the test. So yeah. So it actually the numbers aren't necessarily that good, especially when you break up your information into such small time bits, as Will's going to point out in a moment. So actually getting to essentially what Will's going to be discussing, one such way to do this is the expectation maximization algorithm. And so just to really solidify everything that we're trying to achieve here, the question is, can we reconstruct the accretion history of the galactic halo or the galaxy from stellar distributions in 2D metallicity space? And so I can tell you, as I mentioned a couple of slides back, that you can actually look at these distributions and make some coarse points about where certain contributions to the halo came from, the type of galaxies that contributed. So I know that uniquely stars in this region come from low mass systems, and so this is a lower mass system. I also know here, because of just the way that the template's looked at, if there's going to be a contribution from even lower mass system here, it's going to be in this region. So we know in a coarse way how these galaxies could contribute to this whole metallicity distribution. The real question is, can we get a finer account of how the galaxy was constructed? And so with that, I'll leave the rest of that explanation to my colleague.
So, given all these templates that we have, we proposed a generative model for the observations, these guys, and we say that for each observation, it is generated from one of m mixture components, shown here on the left. Again, these mixture components, as we discussed earlier, are from 1,500 simulated satellites, whereas when we do observations, this is from a smaller subset. So the model that we are using to fit the observations is much more general than the actual observations themselves. And since each of these mixture components has an associated time-since accretion range and mass range, we can actually reconstruct the formation history of the halo if we know what percentage of observations came from each of these mixture components. In a little more detail, if we let x be alpha over fe and y be fe over h, our model, given m mixture components, is as follows. It is a weighted sum of the m mixture components, where the mixture proportion is denoted by pi j, and that denotes, again, the percentage of the observations that come from that particular mixture component. And the mixture component fj is one of the given components that Duane showed you earlier. In the previous illustration, I showed you the case of 4, and Duane showed you the case of 25. The mixing proportions themselves have to sum up to 1, and each one must be greater than or equal to 0. So we ran this model for 2 overall sets. We did a 5x5 grid of mixture components, shown on the left, and we also ran a number of 2x2 grids, shown on the right, with 4 mixing components. The idea being that the choice of a 5x5 grid was somewhat arbitrary. It was based on some astronomical intuitions, and we thought that we might be able to get better results if we did a 2x2 grid, especially because we want to have a method that works with a small number of observations. We don't want to require, say, 500,000 observations. That wouldn't be very useful. So these are some results for the 5x5 grid. We have the true values of pi, which are the mixing proportions, which we know since this is simulated data. And we have our estimated values, which are plotted as green crosses, along with some confidence intervals. As you can see, the true values lie within 2 standard deviations of our estimated values in all the cases, even when the mixture components or the mixing proportions are rather small. So if we have a mixture component that contributes a half a percentage point of overall luminosity, we're still able to recover that accurately. We didn't have success with all halo realizations for a 5x5 grid, so when we switched to a 2x2 grid, we actually saw really good results. Here I've plotted the absolute differences between our estimated values of mixing proportions and the true values on the left for all 11 halo realizations. So that means there are 44 points here. And as you can see, the absolute differences are relatively small. On the right, we have the percentage differences. They're slightly larger, but in general, we don't have anything off by orders of magnitude. So we're able to reconstruct the true mixing proportions fairly well. These 2 outliers you see at the top that are 100% off are because the true values are 0, whereas our algorithm gave us something along the range of 10 to the minus 20. So it's off by a lot, but we think that's okay. So how did we get these mixing proportions?
Tell us what was the complication with the 5x5?
Sorry?
What was it that went wrong with the 5x5?
We think the grid was too granular. Basically, the grid was very specific, and our choice of 5x5 was motivated by the fact that we thought 25 mixture components was a good number. And so we partitioned the mass and time since accretion range fairly equally, and just ran it. It turns out that if you look at all of the simulated data, you can see that a lot of the simulated halos in certain mass ranges are very similar, and so it's pretty much impossible to tell the difference between them. So to estimate the mixing proportions, a natural approach would be to use maximum likelihood, which in our case, well, maximum likelihood is basically a way to find out the most likely estimate. If, let's say, you have a normal density characterized by some mean mu and some variance sigma, maximum likelihood allows you to pick those 2 parameters that maximize the joint probability of all the data. In our case, that means that our maximum likelihood estimate is the argmax with respect to pi of our log likelihood, which is pictured here. This is pretty simple to derive from our model definition. Unfortunately, we can't really differentiate this with respect to pi. So standard maximum likelihood techniques aren't going to work. But expectation maximization provides a way for us to do this. Suppose that we knew which mixture component fj each observation came from. We could then construct what we call a latent indicator variable called zij that is 1 if data point I comes from mixture component j and 0 otherwise. If we have this, we can then express a complete log likelihood in this form, which, as you can see, is much easier to differentiate with respect to pi. So then we can easily get an estimate for the mixing proportions. Unfortunately, we don't know the values of this latent indicator variable, but it's not a problem with expectation maximization. What we do is we replace this unknown latent variable z with the expected value of z conditioned on our data and on the previous value of the mixing proportions. What that means, expectation maximization is an iterative approach, and so at each time t, we get an estimate for the mixing proportions, we get the argmax with respect to pi and the expected value of the log likelihood. Again, with the log likelihood, we replace z with the expected value of z.
How do you start with the expected value at the beginning? Yes.
Good question. We pick random numbers, and it turns out our algorithm is completely insensitive to initialization. We can use random numbers, we can use uniform numbers. It doesn't matter at all. It always converges to the same values. So we just pick random values. It's a two-step algorithm. First step is to find the expected value of the latent variable z. So we can have a log likelihood that we can take the argmax of. We repeat this until our log likelihood stabilizes. In our case, we picked a range of 10 to the minus 4. This was arbitrary. We let it run for longer and nothing really happened. So in a little bit more detail, when I say we find the expected value of the log likelihood using the current expected value of the latent variable, it sounds a little vague. What we're really doing is evaluating this guy here. This is actually just the log likelihood we saw before, with Zij replaced by the expected value of Zij. And since this latent variable is an indicator, its expected value is simply the probability that point I comes from model J, which, using the definition of conditional probability, we can express in a neat little analytical form. We then take this value of Zij, and we can plug it back into our log likelihood, and take the argmax with respect to pi, and analytically, at each time t, this is our estimate of the mixing proportions, which is very easy to compute. You can see this Wij is just the expected value of z from the previous slide. And we got pretty good results with this view to 1,000 observations. With more data, we can have narrower confidence intervals, and we can be more confident in, like I said, we're insensitive to initialization of pi. One common criticism of the EM algorithm is that it's quite slow to converge. In our case, for a 2x2 grid, it took about 60 iterations to converge. And in the case of a 5x5 grid, like the ones that Duane showed you originally, it took about 600 iterations to converge, which is a while. But we did identify large weights after about 10 iterations. So if you look at the plot on the right, these lines are a little faint, but you can see that after about 10 trials, there isn't a whole lot of change going on. This again is percent change in mixing proportions. And after 20, it's very, very flat. Also, I should say that for 60 iterations, it takes 0.3 seconds to run. So I think that's pretty quick. And again, it always converges. So we ran the algorithm many, many, many times, and we never had the problem of one mixing proportion was 5% one time and 27% the next time. We always converged on the exact same answers. So given that we have some estimates of these mixing proportions, it would be useful to have at least confidence intervals. We were actually able to reconstruct full covariance matrices for these mixing proportions. We know that the asymptotic covariance matrix of pi hat can be approximated by the inverse of the observed Fisher information matrix, which I'm sure you all know. And in this form, which is not too tough to calculate, we can then, of course, get the variance and the correlation. This is a plot of one of the 2x2 results. Again, we have the true values of pi as the circles, the estimates as the crosses, and 1 and 2 standard deviation confidence intervals. You can see that the true and estimated values are very close, and the true value is always within 2 standard deviations. We also did n out of n bootstrapping and got essentially the same results at a 95% confidence level. Since we had the full covariance matrix, we are also able to calculate correlation. Again, we did this using the Fisher information method that I showed earlier, along with n out of n bootstrapping, and we got almost exactly the same results. These two plots, the one on the left is for the 5x5 grid, and the one on the right is for one of the 2x2 grids. The larger the dot, the bigger the correlation. Negative correlations are red, positive ones are blue. You can see that the closer two mixing proportions are to each other, the closer two mixture components are to each other, in general, they have slightly larger correlations. This makes sense because we gridded up the time since accretion and the mass range sequentially, and so if two mixture components are next to each other, they have similar time since accretion and masses. Ideally, these of course would all be small. But so in conclusion, we were able to reconstruct the formation history using a 2x2 grid very well with a single finite mixture model. We trained this model on a global set of data, so we used all of the information we had from simulations to create one model, and then we generated 11 random halo realizations using smaller subsets of our data. We ran it through the model, and we were able to reconstruct formation history. It was relatively quickly. It didn't take us very long. We didn't have problems with small values of pi. So if, let's say, one of our mixture components contributed 50% of the mass, we were able to identify it just as quickly as if it had contributed 0.5 percentage point. And our method scales, so we can change the number of mixture components and the amount of data very easily. As far as confidence intervals and covariance matrices, we used two separate methods that produced essentially the same results, which is quite promising. As far as improvements, there are two main avenues that we're working on right now. One of them is adaptive partitioning of the mass and time since accretion. When we make these sets of mixture components, we're just kind of drawing lines somewhat arbitrarily. And as I mentioned, for the 5x5 grid, we had the problem where sometimes these different mixture components were essentially the same. So we have several methods that allow us to adaptively partition so that we set the partitions to maximize the distance or the difference or something like that between the different mixture components. We're still in the early stages, but we have some promising results. And another improvement that we were thinking of doing that might increase the accuracy of this would be to take the 1500 simulated metallicity curves that you saw at the very end of Duane's presentation and to directly smooth them using some sort of weighted kernel smoothing, and then to construct a mixture model with those 1500 components. That approach would also be compatible with adaptive partitioning.
So just want to end with some final comments, and that is to say that the 2D metallicities are a start. This is a great proof of concept. There's things that you can actually, we believe we can actually do with this now, as evidence of some of the results. But there are more dimensions to come, and so this is kind of a burgeoning field of subfield of galactic archaeology. And so, in terms of dimensions, it's more chemical abundances for different particular types of processes that go on. So, in terms of supernovas going off, there's processes that produce certain chemicals or elements, and others that produce others. And so, with those more dimensions, we can actually make even finer splits in terms of the environments from which those stars were created. In addition to that, our methods show and strengthened by these larger data sets. So there are a number of surveys that are slated such that we're looking to get 2 to 3 levels of magnitude in terms of the number of stars we have now, which is for the halo roughly 1,000 if you're talking about good chemical abundance data, but we're looking to increase it to perhaps 10,000 and maybe 100,000 within the end of this decade. And then finally, adding a more physical interpretation of the models will perhaps allow us to sort the galaxies, and so that might help improve our model templates and essentially, well, improve what we can Okay, so the data set comes from Bullock and Johnson 05. So these are, right now it's just all simulated data. And like I mentioned before, they had simulated 11 different halos using a semi-analytic chemical.
Understand the simulation.
Right.
Weren't you comparing this against a sample of stars or not?
Oh, no. Okay. How do we generate the sample of stars? So the essentially we took the actual distribution. So there's star particles in these simulations, and those star particles have alpha over Fe over H metallices associated with each star particle as a part of the halo that's created. And so and those in fact come from the accreted dwarfs. And so what we do is we look at the halo, and then essentially based off of the cumulative distribution function of the luminosity of dwarf contribution, we randomly choose from that to reproduce the stellar observations from that halo. So what that ensures is that you get the right proportions of stars contributed from low mass dwarfs, which is a very low number, to the most massive dwarf, which gives you the bulk of the stars that you see in that distribution. And what's amazing about this technique is that, as Will pointed out, if it's 50%, if it's 1%, it doesn't matter, because it really focuses on the fact that these stars populate different parts of that 2D metallicity distribution.
You said that your 2x2 was physically motivated when you decided the 5x5 wasn't working very well.
Well,
And am I right? Is that what you said? Am I right about that? So,
yes.
this thing is so fast. Why bother? Why not just try a whole bunch of different combinations and see which gives you the best results in the end anyway?
That's one of the ideas we have.
Oh.
Yeah. That's right. Exactly.
I mean, you said it's time consuming, but it didn't look very time consuming.
Yeah, it's not
just
time.
converges so quickly,
No.
you don't have to worry about that. So you can explore the whole space pretty quickly.
Yeah. Sorry. Oh.
If you were to do that, like this adaptive partition, how do you, have you thought about how to handle the number of partitions as a parameter? Just introduce some kind of complexity thing?
We could. I think right now we're thinking of just picking some arbitrary numbers for that, but we definitely could use some. There are many statistical techniques to do that.
I would also add that at some point in time, it becomes unreasonable in terms of the actual data that's out there. So the ability to you kind of narrow these time bins, for instance, or at some level, there's just not enough information to make such fine distinctions between dwarfs that accrete. So right. So that also limits the number of bins. We're not going to 1,500 by 1,500. Right.
Okay.
Oh, yeah.
Yeah,
Oh,
good way.
yeah.
Can you, or have you thought about adding sort of spatial information? For example, food cone in groups, and that obviously gives you very strong evidence that there's a particular remnant in that string right there.
Yeah, no, it's very interesting. I actually got that precise idea yesterday. I can't remember why from what talk, but that's exactly what I was thinking of. So our first.
Hopefully it was by talk.
Yeah, no, I actually, it might have been, but our first idea was, it's simply kind of zero order. You scrap. You don't worry about the, like I said, this phase-based information. But clearly, as when you look at the simulations, even though you don't have like these streams per se, there's still some information in terms of the distribution of those stars in general. So maybe when they accrete early on, there's some extra constraints because many of those stars will live in these streams. But if they accreted, if they accreted later on, if they accreted earlier on, there might be more of this smooth distribution, but there might be some constraints in terms of you know, the extent of that. And so I think that, yes, there is an extra.
I'm looking forward to Gaia, where you're gonna have proper motion for so many stars.
Right, right, absolutely, yeah. So it would be,
Great data set.
you got it, yeah, that and with Moss,